Spherical Cow Philosophy. Conservation laws are obviously both conceptually important and practically useful. But there is another reason why they, and conservation of momentum in particular, are an appropriate starting point for an exploration of the physical world. They illustrate a basic methodological principle, the Spherical Cow Philosophy. The name comes from a joke that the physicists like to tell about themselves. A dairy farmer is struggling with milk output at the farm and decides to ask a scientist at the local university for help. For reasons that remain unexplained, they consult with a theoretical physicist. The physicist goes off to do some complicated calculation and returns with an impressive-looking stack of equations. "I solved your problem, I think," says the physicist. "What is it?" replies the farmer excitedly. "Well, first assume a spherical cow." The humor value, in case it's not immediately obvious, lies in the fact that not only are cows not spherical, but also that their non-spherical nature is crucial to what it means to be a cow. A spherical cow wouldn't be a cow at all. Making that assumption might simplify the calculation a physicist might want to do, but in doing so it removes us entirely from the realm of insights that would actually be useful to the dairy farmer. The joke is famous not because it's side-splittingly funny, nobody ever claimed that, but because the equivalent of assume a spherical cow actually does work in physics, and it works incredibly well. It's an example of a general principle, namely, idealize a difficult problem down to a simple one by ignoring as many complications as you can. Get an answer to the simple problem, then put the complications back in and calculate how they affect the answer to the simple problem. This way of thinking is how we invented conservation of momentum. Aristotle wasn't wrong. Coffee cups don't start moving by themselves, and if you push them for a while and then stop, they will quickly come back to rest. But Ibn Sina wasn't wrong either. The cup comes to rest because of friction, not because of its intrinsic nature. If we can ignore friction and imagine an arrow flying through vacuum, it would continue moving at a constant velocity. That's the starting point for a useful physical analysis. We can always add the complications of friction back in later. The master of this kind of reasoning was Galileo. He had a genius for figuring out what things were essential and what could be ignored at the first pass. Aristotle had claimed that heavier objects fell faster than lighter ones. Again, not wrong. Drop a book and a single piece of paper at the same time and see what your experimental results reveal. But Galileo argued that if there were no air resistance, they would fall at the same rate. That's an experiment no person could actually perform until centuries later, but Galileo was able to construct ingenious experimental setups that were able to establish the underlying principle. We will see the spherical cow philosophy at work again and again. But as useful as it is, it's not a universal truth-finding method. It does not work that well in dairy farming, for example. In many complex systems, such as we often encounter in the macroscopic human-scale world, different aspects of the underlying situation interact in crucial ways with one another, such that you cannot just ignore them one at a time and correct for their effects later. In fields like biology or economics, everything often depends on everything else. The reason why physics seems so hard is because it actually is quite easy compared to other science. In physics, at least in some parts, we have this miraculous ability to set aside various components of the system we are thinking about, solve a much simpler problem, and put everything back together at the end. That makes our life enormously easier than it otherwise would have been. As a result, Physicists are able to discover amazing and counterintuitive features of the world, from quantum mechanics to relativity to the Big Bang. We would never have been able to just guess these things by being clever. We were forced to invent them by trying to fit the experimental data. But precisely because they are so counterintuitive, they can be hard to understand, at least at first glance. If the vista before us seems alien, it is because we are looking so very far.